Welcome to the recording of a lesson on L'Hopital's rule, spelled L'Hopital. So L'Hopital's rule, which deals with limits. As you go through this, you are encouraged to pause the recording from time to time to attempt the problems and then check your work. Before we go over L'Hopital's rule, need to go over limits since L'Hopital's rule is a way of dealing with what are called indeterminate limits. So you might want to attempt these three problems and look back at your notes before beginning. So for the first problem, for the limit as x approaches 3 of x squared minus 2, first step for a limit is usually just to try substituting the number. So if we substitute, we get 1 over 3 squared minus 2. So 3 squared minus 2 is 7, so that's 1/7, and we can leave that as an answer. You could write that as decimal, however, you don't have to. So now let's take a look at the limit as x approaches 4 of x minus 4 over x squared plus 3x minus 28. If we plug in 4 for x, we get on the top 0 and on the bottom 0. So that is 0 divided by 0, which you may recall from earlier in the course does not have a value and cannot be left as a final answer for a limit. So if that is the case, one technique that we can use is to simplify the fraction. So doing that, we can rewrite the top as 1 times x minus 4, and we can factor the bottom to being x plus 7 times x minus 4. In this case, we can cancel the x minus 4's, and we are left with 1 over x plus 7, from which we can plug in 4 to get a final answer of 1 over 11. You also may recall that we can calculate limits based on a graph. So on the final problem on this intro, to calculate the limit based on a graph, we follow the graph to where it approaches, not where the point is. So if we are finding the limit as x approaches 2 of the function given on the graph, we note that as we approach 2 horizontally along the slanted line, we end up at the open circle with y equals 4. This gives us an answer of 4. We now come to a different function that poses its own issues, and that is we are going to consider the limit as x approaches 0 of sine of x divided by x. So for this, if we plug in, sine of 0 is 0, and we're dividing by 0, which gives us 0 over 0, and that is indeterminate, meaning we cannot leave it as an answer for a limit. However, in this case, there's no way to factor or simplify sine of x over x. So we need a different way. One thing we can do is we can look at the graph and we can solve it using the graph. So the graph of y equals sine of x over x is shown. And on the graph, if we look at where the curve goes as we approach x equals 0, which is the y-axis, the curve approaches 1. So that gives us the limit as x approaches 0 of sine of x over x is equal to 1. That's fine if we have a graphing utility, which we may not, and also we may not trust our graphing utility because, again, this is entirely possible to make a mistake entering a function that could then affect an answer like this. So we now consider the case that we don't have a graphing utility to use to calculate the limit as x approaches 0 of sine of x over x. Well, it is possible to create a graph by hand. This is time consuming, and this gives a lot of opportunities for errors. So as it turns out, there is a helpful rule for this, and that is L'Hopital's rule. L'Hopital's rule states that anytime we have a limit that results in an indeterminate fraction, which means either 0 divided by 0 or infinity divided by infinity, we are allowed to take the derivative of the top and the bottom of the fraction and then reevaluate the limit, meaning try plugging in the number again. If we do this for sine of x over x, we note that plugging in 0 gives us 0 over 0, which allows us to do this. The derivative of sine of x is cosine of x, and the derivative of x is 1. If we now plug in x equals 0 into our new fraction, we have cosine of 0 over 1, where cosine of 0 is 1, and so 1 divided by 1 is equal to 1, which gives us the correct answer to this limit without graphing. Here are some practice examples. Please note that some of these will require L'Hopital's rule, others will not. You are encouraged to attempt these before watching the recording, as it may help you understand what has gone over better. So feel free to pause the recording at this time if you wish. So before we can even think about using L'Hopital's rule, we have to substitute the number for x into the limit and verify that it is either 0 over 0 or infinity over infinity. Doing so for the first one, we get sine of 5 times 0 over 2 times 0. So sine of 0 is 0, and 2 times 0 is 0. This gives us 0 divided by 0, which means that we are able to use L'Hopital's rule. And in this case, we pretty much have to. Using L'Hopital's rule, we take the derivative of the top and the derivative of the bottom of the fraction separately. The derivative of sine of 5x is equal to 5 times cosine 5x. This is a chain rule. The derivative of the bottom of the fraction, derivative of 2x, is 2. Once we have done this, we plug in the number for x, and we get 5 times sine of 5 times cosine of 5 times 0 divided by 2. Cosine of 0 is 1 times 5 is 5. On the bottom it's 2, which gives us an answer of 5 over 2. We can then move on to the next one. Similar to the first one, if we plug in 0 for x, we note that cosine of 0 is 1, so we got 2 minus 2 times 1, so 2 minus 2 on the top, which is 0. We also note that e to the 0 is 1, as raising any number other than 0 to the 0 power results in 1. So this gives us 2 minus 2 over 1 minus 1, which gives us 0 over 0. So, similar to the first one, we can then use L'Hopital's rule and take the derivative of the top and the bottom. The derivative of 2 minus 2 cosine x is 0 plus 2 sine x. The derivative of cosine is negative sine, and the negative and the other negative cancel out. On the bottom, the derivative of 1 is 0, and the derivative of e to the x is itself. So, this gives us 2 sine x over e to the x, from which we can plug in 0. Sine of 0 is 0, and e to the 0 is 1. This gives us 0 divided by 1, which is 0. As a reminder, if you have 0 cupcakes divided by one person, that person gets 0 cupcakes. So be careful about the distinction between 0 divided by 0 and 0 divided by a non-zero number. For the last one, if we plug in 0, sine of 0 is 0, and e to the 0 is 1. So this is 0 divided by 1, which is not indeterminate. The answer to this is just 0, and you do not use L'Hopital's rule for this last one. Take a look at another situation involving L'Hopital's rule that ends up being slightly different than the other ones. So we're taking the limit as x approaches 0 of e to the 3x minus 1 over x squared. We start out by plugging in 0 for x, which results in 0 over 0 after doing some arithmetic. So that means we then use L'Hopital's rule. So the derivative of the top is 3e to the 3x minus 3, and the derivative of the bottom is 2x. We try plugging in 0 for x again. However, we are left with 3 minus 3 on the top and 0 on the bottom, which gives 0 over 0, which means it's still indeterminate. In this case, we have to use L'Hopital's rule again. Taking another derivative of the top results in 9e to the 3x minus 0, which is just 9e to the 3x. And the derivative of 2x on the bottom is 2. Now, if we plug in 0, we get 9e to the 3 times 0 over 2, which ends up being 9 over 2, which is our answer to this problem. There are other forms other than the fraction. There are other forms other than 0 over 0 or infinity over infinity that are indeterminate, meaning that we cannot leave limits in these forms. It is suggested that on your own, you plug in the numbers into the limits given to see what they equal without actually looking up the limits, and then compare your answers to what is on the lower right. So for the first limit, if we plug in 0 for x, 1 over 0 squared is infinity, so we end up with infinity times 0. On the second limit, we also end up with infinity times 0, since 1 over 0 squared is 0, and, well, correction, 0 squared is 0, so 1 over 0 is infinity, times 0 squared, this also is infinity times 0. For the next one, if we plug in infinity, 1 plus 1 over infinity is 1, because 1 over infinity is 0. And then that is raised to the infinity power, giving 1 to the infinity. The last one is also 1 to the infinity. Now, hopefully you notice that you have two pairs of limits that when plugged in appear to be the same. However, using graphs, you will find that for the first one, the limit as x approaches 0 of 1 over x squared times x cubed is actually 0. And whereas the second one, limit as x approaches 0 of 1 over x squared times x squared is actually 1. So despite both of them plugging in to being infinity times 0, they have different values. For the third one, using a graph, you will end up with about 2.718 for the limit as x approaches infinity of 1 plus 1 over x raised to the x. On the other hand, the limit as x approaches infinity of 1 to the x is just 1. So similar to infinity times 0, 1 raised to the infinity gives limits with different values. So there are other indeterminate forms other than 0 over 0 or infinity over infinity. These are indeterminate forms include 0 times infinity is indeterminate, 0 raised to the 0 is indeterminate, 1 raised to the infinity is indeterminate, infinity raised to the 0 is indeterminate, and infinity minus infinity is indeterminate. When it comes to limits, none of these answers can stand. However, we won't deal with very many of these, and some of these occur very seldom in practical applications. However, the key idea is that in order to use L'Hopital's rule, the limit must be written as a fraction, meaning we cannot just take derivatives if we get 0 times infinity, 0 to the 0, 1 to the infinity, 0 infinity to the 0, or infinity minus infinity. We have to find some way of writing that limit as a fraction. This ranges from not particularly difficult to, in some cases, very difficult, or even algebraically just not worth doing. We will now look at 3 examples. Please note that only the first example will be ever required for a problem like this on a test or homework. The next 2 will only appear on extra credit. So if you are either too tired or if you feel overwhelmed, you are welcome to stop the recording and not watch for the demonstration of the second and third examples. For the first example, limit as x approaches infinity of x times 2 to the negative 3x. If we plug in, we get infinity times 0, since 2 to the negative infinity is equal to 1 over 2 to the infinity, which is 0. Because this is infinity times 0, it's indeterminate. Now, we are looking at 2 to the negative 3x, meaning we can rewrite this limit as x divided by 2 to the 3x. Now, at this point, we have it in fractional form, and we know that if we plug in infinity for x, we get infinity over infinity, meaning we may use L'Hopital's rule. Using L'Hopital's rule, the derivative of x is 1, and the derivative of 2 to the 3x is 2 to the 3x times natural log 2 times 3. Plugging in infinity for this, we get 1 divided by infinity, which is 0. And at this point, we are done, and this limit is 0. That is the last problem that will ever be required on a quiz or test from this recording. For those that wish to move on, consider the next one, where we have the limit as x approaches 0 of x squared times ln of x. Plugging in 0 results in 0 times negative infinity, which is indeterminate. In this case, we have to rewrite x squared as x to the negative second, put it in the denominator. Now, from here, if we were to plug in 0, we would get negative infinity over infinity, meaning we may use L'Hopital's rule. Now, using L'Hopital's rule, the derivative of ln of x is 1 over x, and the derivative of x to the negative second is negative 2x to the negative third. We can rewrite a fraction as division. So in this case, we have the limit as x approaches 0 of 1 over x divided by negative 2 over x cubed. Using the rule for division of fractions, whereby we take the reciprocal, meaning the second one flipped, and multiply, this becomes the limit as x approaches 0 of x cubed divided by negative 2x. At this point, we can cancel one of the x's, and it becomes the limit as x approaches 0 of negative x squared over 2. Plugging in 0 gives negative 0 squared divided by 2, which is 0. For the last one, it is significantly more complicated. In order to get an exponent to no longer be an exponent, and instead get it to be multiplication, we need logarithms. To use a logarithm on a problem, we need to use its inverse as well, meaning the best route for us here is to take e to the natural log of the limit, because e and natural log are inverses, and if we apply both, we can get the same answer. Now, once we have written it as e to the natural log, we can use properties of logarithms and move the exponent out in front of the natural log, which results in e to the limit as x approaches infinity of 5x times natural log 1 plus 4x to the negative 1. To rewrite this as a fraction, we use a similar technique to the previous problem and bring the x to the bottom as x to the negative 1. Now, for the limit portion of this, we have the limit. If we plug in infinity, we get 0 over 0, or correction. We get infinity over infinity, which then, correction again. Sorry, everybody. If we plug in infinity, we get infinity to the negative 1 is 1 over infinity, which is 0. So we have 0 in the denominator. And on the top, we have natural log 1 plus 0, and natural log of 1 is 0. So this gives us 0 over 0, meaning we may use L'Hopital's rule on the limit. Using this, the derivative of 5 times ln 1 plus 4x to the negative 1 is 5 over 1 plus 4x to the negative 1 times negative 4x to the negative second. The derivative of x to the negative 1 is negative x to the negative second. Now, from this, we can cancel out the x to the negative seconds, and also we can rewrite the denominator of the top part as 1 plus 4 over x. Plugging in infinity, we get 4 divided by infinity is 0, meaning we have 20 divided by 1, which results in e to the 20, which is our final answer. Fortunately enough, that is all. So everybody, have a great day. Thank you for watching.